out in the vast silence of space, a radio telescope picks up something extraordinary, a rapid, rhythmic pulse cutting through the cosmic noise with unnatural precision. These aren't random bursts, they arrive like clockwork, so exact they could be mistaken for a cosmic metronome. Scientists call them pulsars, the spinning corpses of dead stars, denser than anything we can imagine. But what if these celestial beacons aren't just natural phenomena? What if, hidden in their precise patterns, lies something far more astonishing, a message? For decades, a daring theory has whispered through the halls of astronomy that these pulses might not just be the heartbeat of dying stars, but deliberate signals from an intelligence beyond our world. Tonight, we're diving into one of space's greatest mysteries. Our pulsar codes the universe's way of saying we're not alone. The story begins in 1967, when a young graduate student named Jocelyn Bell Burnell was sifting through reams of radio telescope data at Cambridge University. She spotted something no one expected, a strange, rhythmic signal repeating every 1.337 seconds with astonishing precision. At first, the pattern seemed too perfect, too mechanical, to be natural. In fact, the signal was so uncanny that Burnell and her advisor, Anthony Hewish, jokingly labeled it LGM-1, short for Little Green Men. Could this be the first sign of extraterrestrial intelligence attempting to make contact? But as more of these signals were detected across the cosmos, the truth became clear. These weren't messages from aliens. They were the cosmic lighthouses we now call pulsars. What Burnell had stumbled upon was the spinning core of a collapsed star, a neutron star, so dense that a single teaspoon of its material would weigh 1 billion tons. As it rotates, it beams radiation into space like a celestial strobe light, producing the exact pulses that first fooled scientists into considering alien origins. Yet, even after the natural explanation emerged, the mystery didn't entirely fade. The sheer regularity of these pulses, their mathematical perfection, left some wondering, could nature really produce such flawless rhythm, or was there still something more to uncover? The discovery of pulsars reshaped our understanding of the universe, but it also sparked a debate that still lingers today. If these signals had briefly fooled some of the brightest minds on Earth, what else might we be missing in the vast, silent expanse of space? Here's the next segment of your script. At their core, pulsars are some of the most extreme objects in the universe, cosmic relics born from violent stellar explosions. When a massive star reaches the end of its life, it doesn't fade quietly. Instead, it goes out in a cataclysmic supernova, a blast so powerful it can outshine an entire galaxy for weeks. What remains after this cosmic detonation is a neutron star, an unimaginably dense leftover, packing more mass than our entire sun into a sphere no wider than a city. But here's where things get even more fascinating. Not all neutron stars become pulsars, only those with a particular cosmic quirk. As these collapsed stars spin, their intense magnetic fields funnel radiation into narrow beams, like a lighthouse cutting through the dark. If one of those beams happens to sweep across Earth, we detect it as a pulse, an unbelievably steady tick, some flashing hundreds of times every second, with precision rivaling atomic clocks. It's this eerie regularity that first made scientists question whether these signals were natural at all. Imagine hearing a drumbeat in space so exact you could set your watch to it. No wonder some initially thought they were picking up alien transmissions. Yet, as bizarre as these objects seem, their behavior follows the elegant laws of physics. The faster a pulsar spins, the quicker its pulses arrive. Some slow down over millennia, like a cosmic top winding down, while others, called millisecond pulsars, whip around at dizzying speeds, accelerated by siphoning material from companion stars. What makes pulsars truly mind-bending is their density. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest, compressed into an atomic-scale soup where matter stops behaving normally. Electrons and protons are crushed together so tightly they merge into neutrons, hence the name. Under those insane pressures, the very fabric of matter warps into forms we can scarcely replicate on Earth. And yet, despite their extreme nature, pulsars serve as some of the universe's best navigational tools. Astronomers have used their clockwork pulses to test Einstein's theory of relativity, map the Milky Way's magnetic fields, and even guide spacecraft. They are natural cosmic laboratories, pushing the boundaries of what we know about physics, while still keeping a few mysteries up their sleeves. Could there be patterns within their pulses we haven't yet decoded? Or are they simply nature's way of showing us just how strange and precise the cosmos can be? This segment keeps the narrative flowing smoothly, expands on the science without overwhelming the audience, and maintains an engaging, conversational tone. Let me know if you'd like any refinements. One summer night in 1977, a radio telescope in Ohio picked up a signal so startling that the astronomer who discovered it scribbled, "Wow," in the margin of the printout, and the name stuck. For 72 seconds, a burst of radio waves blared from the direction of the constellation Sagittarius, blazing 30 times louder than the background noise of space. Then, just as suddenly as it appeared, it vanished, never repeating again. To this day, the WOW signal remains one of the strongest candidates for a potential extraterrestrial transmission ever detected. But here's the twist. Its frequency, hovering around 1420 MHz, matches a range scientists speculate alien civilizations might use, and it's eerily close to the natural emissions of pulsars. At first glance, the WOW signal seems nothing like the steady, rhythmic pulses of a neutron star. Pulsars are predictable, ticking away like cosmic timepieces, while the WOW signal was a one-off event, wild and unexplained. Yet dig deeper and curious parallels emerge. Both phenomena occupy a radio frequency range known as the water hole, a quiet band between the noise of hydrogen and hydroxyl molecules, where interstellar signals could theoretically travel vast distances without too much interference. It's as if someone, or something, chose the perfect cosmic channel to shout into the void. Then there's the question of precision. The WOW signal's intensity followed a distinct curve, rising and falling in a way that mirrors how a distant beacon would appear as Earth's rotation swept a telescope's gaze across it. That kind of pattern doesn't happen randomly. Natural cosmic static doesn't behave so cleanly. Some researchers argue the signal's structure leans suspiciously toward artificiality, like a brief, intentional broadcast rather than a celestial accident. Of course, skeptics have other explanations. Could it have been a rogue comet reflecting radio waves, a glitch in the telescope? The problem is, none of these theories fully account for the signal's intensity or its peculiar frequency. And while pulsars weren't the source, they don't just blink once and disappear. The WOW signal's lingering mystery keeps the door cracked open. What if it wasn't a natural phenomenon at all, but something more deliberate? A fleeting attempt at contact, or even a fragment of a larger, unrecognized pattern? This is where the pulsar code theory takes an intriguing leap. If advanced civilizations exist, might they use neutron stars as cosmic lighthouses, not just as navigational markers, but as relays for communication? Imagine encoding a message into a pulsar's pulses, tweaking their timing or intensity in ways that stand out against nature's rhythm. The WOW signal could have been a test, a stray fragment of a far more complex transmission system we're only beginning to imagine. Or perhaps it was something else entirely, a cosmic coincidence that continues to taunt us with its ambiguity. One thing's certain, decades later, the WOW signal still defies easy answers. Whether it was a natural oddity or something more profound, it reminds us that the universe is full of voices we've yet to understand. And pulsars, with their uncanny regularity, might just hold the key to deciphering them. What if the universe's most precise clocks occasionally stutter? Pulsars are renowned for their flawless rhythms, but every so often, something strange happens, their beats falter. Without warning, a pulsar's spin might briefly speed up or slow down, as if an invisible hand tweaked its cosmic metronome. Astronomers call these events glitches, and while most dismiss them as natural quirks of extreme physics, a provocative question lingers. Could these anomalies be more than just stellar hiccups? Take the Vela pulsar, a neutron star spinning 11 times per second in the southern sky. In 2016, it abruptly sped up by a fraction of a second, a tiny shift, but enough to defy standard models. Scientists theorize that these glitches occur when the star's crust, strained by its mind-bending rotation, suddenly cracks and settles, like tectonic plates on an overclocked planet. Yet not all glitches fit neatly into this explanation. Some pulsars slow down instead, their pulses arriving microseconds later than predicted, as if something were subtly breaking their spin. Then there are the nulling pulsars, ones that occasionally skip beats altogether, their signals vanishing for minutes or even hours before resuming as if nothing happened. Imagine a drummer missing a stroke mid-song, then picking up the rhythm flawlessly. Natural, maybe, but here's the puzzle. A handful of these pulsars exhibit patterns in their silences, like a coded pause between words. Mainstream astrophysics attributes these oddities to chaos beneath a neutron star's surface. Superfluid vortices tangling, magnetic fields rearranging, or starquakes rippling through its ultra-dense crust. But the sheer variety of anomalies has fueled alternative theories. Could an advanced civilization, for instance, manipulate pulsar signals as a way to broadcast information across galaxies? Encode data in timing delays, or use glitches as markers in a vast interstellar network? The idea isn't entirely science fiction. If humans wanted to send a message detectable across light years, embedding it in an existing cosmic beacon, one that outlasts civilizations, would be ingenious. Pulsars, after all, are nature's megaphones, their signals audible for millennia. A deliberate glitch might stand out against natural noise, like a flickering street lamp catching your eye in the dark. Of course, extraordinary claims require extraordinary evidence, and so far, every pulsar anomaly has a plausible astrophysical explanation. But the very fact that these phenomena challenge our understanding keeps the door ajar. As telescopes grow more sensitive and AI sifts through pulsar data for subtle irregularities, who knows what patterns might emerge? For now, these cosmic stutters remain one of space's most tantalizing what-ifs, a reminder that even the universe's most precise machines might still hold secrets. Script segment. In 1974, astronomers made a discovery that would change understanding of the cosmos and push Einstein's theory of relativity to its limits. Nestled in the constellation Aquila, two dead stars were locked in a lethal dance, one a pulsar, the other a silent neutron star, whirling around each other at nearly 1,000,000 kilometers per hour. This was PSRB 1913+16, the first binary pulsar ever detected, and its movements were so precise they acted as a gravitational laboratory in space. As these cosmic partners orbit one another, they lose energy in the form of ripples through spacetime gravitational waves, causing their paths to inch closer together. Here's the astonishing part. Their orbital decay matches Einstein's predictions down to a fraction of a percent, an observation so accurate it earned its discoverers a Nobel Prize. But with such flawless alignment to theoretical physics, a daring question arises: could nature alone produce this level of precision, or does it hint at something more deliberate? The binary pulsar's rhythm is mind-bogglingly consistent. Like a perfectly tuned metronome, its pulses arrive with split-second regularity, allowing scientists to track even the tiniest shifts in its orbit. Over decades, its dance has slowed by mere milliseconds, exactly as relativity dictates. Yet for all its predictability, there's an uncanny elegance to its behavior. If you wanted to demonstrate gravitational waves to an alien civilization, you'd struggle to design a clearer example than this celestial duo. That very perfection has sparked whispers of a wild possibility. Some theorists speculate whether an advanced civilization might manipulate pulsars as galactic signaling devices, using their gravity-defying precision to broadcast mathematical proofs or even coordinates. After all, if you wanted to send a message across millennia, engineering a binary system like PSRB 1913+16 would be an ingenious way to do it. The pulsar's timing would act like a cosmic signature, unmistakable against the noise of random stellar objects. Of course, mainstream science dismisses this as fanciful. The binary pulsar fits seamlessly into our models of neutron star behavior, and its decay aligns precisely with natural physics. But the fact remains, its existence walks the line between cosmic coincidence and something almost tailored for discovery. Whether natural or not, PSRB 1913+16 forces us to confront how much we still don't know, and how the universe, in its strangeness, sometimes feels like it's leaving breadcrumbs for us to follow. Among the steady cosmic pulses of neutron stars, some researchers have detected something that defies simple explanation: mathematical whispers hidden in the noise. While most pulsars tick away with reliable regularity, a handful appear to carry patterns so precise they seem to flirt with intentional design: sequences of prime numbers, echoes of the Fibonacci spiral, ratios that mirror fundamental constants. Could these be random quirks of nature, or something far more deliberate? The idea isn't just speculative fiction. Astrophysicist Paul Laviolette and others have pointed to anomalies in pulsar behavior that resist conventional explanation. Take the Crab pulsar, for instance. Buried in its rapid fire, pulses are intervals that align eerily with prime numbers, figures divisible only by themselves and 1. In isolation, this might seem coincidental, but when multiple pulsars exhibit similar numerical quirks, the odds of pure chance start to thin. Then there's the Fibonacci connection. This sequence, where each number is the sum of the two before it, shows up everywhere in nature, from sunflower seeds to spiral galaxies. Yet when certain pulsars emit pulses spaced at Fibonacci-like intervals, it raises eyebrows. Could these be cosmic breadcrumbs left by an intelligence leveraging universal mathematical language? After all, if you wanted to send a message across the void, encoding it in patterns that transcend culture and species would be a stroke of genius. Skeptics argue these patterns are inevitable in any large dataset, like finding faces in clouds, and they're not wrong. The human brain is wired to seek order, even where none exists. But the counterpoint is equally compelling. Pulsars aren't just any natural phenomenon. Their precision rivals our best atomic clocks, and their signals pierce through interstellar dust with pristine clarity. If an advanced civilization did want to communicate, hijacking these cosmic lighthouses would be an elegant solution, embedding data in plain sight, disguised as stellar physics. One striking example comes from the so-called golden pulsar, whose pulse intervals approximate the golden ratio, mathematical constant tied to aesthetics and harmony. Art, architecture, even DNA spirals adhere to this proportion. So why wouldn't nature's most extreme objects do the same? Unless, of course, it's not nature at work here. The debate hinges on a deeper question. Where do we draw the line between the universe's innate order and the fingerprints of design? For now, mainstream science leans toward natural explanations, attributing these patterns to the complex physics of superdense matter. But the allure of pulsar codes persists, a tantalizing what-if that keeps researchers scanning the stars, listening not just for the beat of cosmic drums, but for the whispers hidden between them. For decades, the search for extraterrestrial intelligence has turned its gaze toward the stars, but not just toward distant planets. Some of the most promising places to hunt for alien messages might not be worlds at all, but the precise, flashing beacons of pulsars. The SETI Institute, alongside researchers like those at Penn State University, has spent years staring into these cosmic strobes, asking one radical question: could nature's most perfect rhythms hide something more? Take the Penn State study that combed through pulsar data with forensic precision. Instead of dismissing their pulses as natural phenomena, scientists analyzed the intervals between them, searching for anomalies that might suggest embedded patterns, mathematical codes, or deliberate irregularities that couldn't arise by chance. They weren't just studying the stars, they were reverse engineering them, treating each pulse like a potential symbol in an alien cipher. What makes this approach so compelling is its simplicity. If an advanced civilization wanted to broadcast a message across millennia, piggybacking on a pulsar's signal would be brilliant. These cosmic lighthouses outlast civilizations, their beams cutting through interstellar noise with unmatched clarity. A slight tweak in timing, a skipped pulse here, a microsecond delay there, could carry information, like Morse code etched into the fabric of space-time itself. Penn State's work zeroed in on this possibility, scanning for sequences that defied randomness, prime numbers, geometric progressions, even echoes of fundamental constants like pi. Any structure that seemed too deliberate to be natural became a red flag. And while no smoking gun has been found yet, the very act of looking rewrites the rules of SETI. Instead of listening for deliberate radio broadcasts, we're now asking whether aliens might have left their mark on the universe's own infrastructure. Critics argue it's a long shot, that pulsar patterns, no matter how strange, can be explained by the chaotic physics of neutron stars. But SETI gamble reflects a deeper truth. In a cosmos this vast, we can't afford to dismiss even the wildest possibilities. After all, the original pulsar discovery was nearly mistaken for an alien signal. If history's any guide, the next big revelation might be hiding in plain sight, masquerading as just another quirk of nature. So while the Penn State study didn't crack an interstellar code, it quietly shifted the goalposts. The search isn't just about finding voices in the dark anymore, it's about questioning whether the universe itself might be speaking to us. one pulse at a time. And if that's true, the greatest message might not be in the stars' light, but in their silence between the beats. Asterisk asterisk script segment. Asterisk asterisk back in 1974, humanity took its first deliberate step toward cosmic conversation, not by listening, but by shouting into the void. From the towering dish of the Arecibo Observatory in Puerto Rico, scientists blasted a 3-minute radio message toward a dense cluster of stars 25,000 light-years away. It was a symbolic hello, packed with binary code depicting our DNA, the solar system, and even a stick figure of a human. But here's the twist: 27 years later, something astonishing seemed to answer back. In 2001, an amateur astronomer analyzing satellite images spotted a strange formation in a wheat field near England's Chilbolton Observatory, a crop circle unlike any other. Instead of the usual swirls, this one bore an eerie resemblance to the original Arecibo transmission, with the same pixelated layout, but with deliberate changes. The human silhouette was altered to resemble a large-headed being, the DNA structure was rewritten, and the solar system diagram pointed to a different star. And right beside it, a second formation resembling a pulsar's signal pattern, complete with a binary code timestamp matching the date the message was found. The internet exploded with theories. Had extraterrestrials not only received our message, but crafted a reply, using Earth's own crops as their canvas? Even more intriguing, some claimed the pulsar-like pattern in the crop circle matched real stellar coordinates that, when traced, pointed toward a neutron star. For a brief, electrifying moment, it seemed like proof that someone, or something, had decoded our cosmic call, but the euphoria didn't last. Scientists quickly debunked the phenomenon. The crop circles were human-made, an elaborate hoax by artists who'd meticulously replicated and tweaked the Arecibo design. The pulsar coordinates, a clever addition, but one that didn't hold up under scrutiny. Yet despite the debunking, the myth of the Arecibo response refuses to die. Why? Part of it's the timing. The crop circles appeared just as public fascination with pulsars and SETI was surging, tapping into our deepest hopes for cosmic companionship. Then there's the unsettling precision of the alterations, like an editor refining a manuscript. The changes felt intentional, almost pedagogical. What if, skeptics whisper, the hoaxers were nudging us to think about how a real alien reply might look? But perhaps the real lesson lies in the psychology behind the hoax's endurance. The Arecibo message was always a long shot, a bottle tossed into an interstellar ocean. The fact that we so desperately wanted a response, even a fabricated one, speaks volumes. It's a reminder that pulsars, crop circles, and the silence between the stars aren't just scientific curiosities. They're mirrors reflecting our own loneliness and our stubborn belief that somewhere in the ticking of those cosmic clocks, someone might still be listening. Picture this: you're adrift in the endless ocean of space, light years from any familiar star. Without landmarks or maps, how would you find your way? For interstellar travelers, pulsars might be the ultimate cosmic guideposts, flashing lighthouses so reliable they could form a galactic navigation network. Their pulses arrive with such precision that even after centuries of travel, their rhythm would remain as dependable as a ticking clock. Here's how it works. Every pulsar has a unique fingerprint, a specific spin rate and pulse pattern that sets it apart from others. By tracking multiple pulsars across different regions of the sky, a spacecraft could triangulate its position with astonishing accuracy, much like ancient sailors using stars, but on a far grander scale. Some of these stellar metronomes are so stable, they lose or gain just 1 second over millions of years. That's a level of reliability no human-made clock can match. In fact, we've already tested this idea. The plaques aboard NAS, a Pioneer probes, and the golden records on the Voyager spacecraft include pulsar maps, diagrams showing Earth's location relative to nearby neutron stars, just in case another civilization someday retrieves them. It's a way of saying, asterisk, here's how to find us, asterisk using the universe's most enduring landmarks. But what if this wasn't just a human innovation? Some theorists propose that an ancient, advanced species might have deliberately positioned pulsars as navigational aids, scattering them like breadcrumbs across the galaxy to guide future travelers. After all, if you were building an interstellar highway, what better markers could you create than objects that outlast civilizations and shine across unfathomable distances? Skeptics counter that pulsars form naturally from supernova remnants, with no need for extraterrestrial engineering, yet their distribution isn't entirely random. Certain regions, like the densely packed heart of the Milky Way, are richer in pulsars, almost like hubs in a vast transportation network. Could that be coincidence, or something more intentional? One compelling case is PSRB 1937 plus 21, a millisecond pulsar spinning so fast it completes hundreds of rotations every second. Its rhythm is so flawless, it rivals atomic clocks on Earth. If you wanted to mark a major crossroads in the galaxy, this would be the ideal beacon, a cosmic buoy blinking with unmistakable clarity. Whether natural or designed, pulsars offer something extraordinary, a way to navigate the cosmos without getting lost in the dark. For now, their signals help astronomers map the Milky Way, but someday they might guide ships between the stars, whether ours or someone else's, returning home along a path lit by the slow, steady pulse of dead stars. *** script segment. *** among the tangled web of cosmic mysteries, few have sparked as much controversy as the so-called Black Knight satellite **, a shadowy object allegedly orbiting Earth, wrapped in layers of myth and misinterpretation. Conspiracy theorists claim this enigmatic satellite has been lurking in our skies for thousands of years, even predating human spaceflight. But what really ties it to our pulsar puzzle? The answer lies in a bizarre detail. Some insist the Black Knight emits rhythmic radio signals eerily similar to pulsar codes. Could this be evidence of an ancient alien probe silently watching us, or just another case of cosmic folklore masquerading as truth? The story took root in the 1950s when newspapers reported strange radio echoes picked up by early satellites, delayed signals that seemed to bounce off something unseen. By the 1960s, amateur radio operators claimed to intercept peculiar pulses, some with intervals mirroring the cadence of neutron stars. Wild speculation followed. Was this an alien artifact left behind by visitors eons ago, still humming with cryptic purpose? The legend only grew when grainy photographs surfaced, showing a jagged, asymmetrical shape drifting near Earth's orbit. Tabloids dubbed it the Black Knight **, and its mythos spiraled into pop culture. Yet every piece of the Black Knight narrative crumbles under scrutiny. Those mysterious radio echoes, scientists later traced them to ordinary ionospheric phenomena, the same atmospheric distortions that once fooled radar operators into thinking they'd detected ghost aircraft. The pulsar-like signals, pure coincidence if they existed at all. As for those infamous photos, they've been debunked as thermal blankets lost during space missions. their twisted metal catching the light in deceptive ways. Even NASA has publicly dismissed the theory, attributing the sightings to space debris and optical illusions. But here's where things get interesting. The persistence of the Black Knight myth reveals something deeper than just a UFO tale. It's a reflection of our fascination with the idea that pulsars, or anything in the cosmos exhibiting unnatural precision, might be more than natural wonders. If neutron stars can mimic artificial beacons so convincingly, it's no surprise we project those same hopes onto rogue satellites. The Black Knight is less about evidence and more about our longing for cosmic companionship, a desire to believe that even in Earth's backyard, the universe might be whispering secrets. So, while the Black Knight itself is almost certainly a modern myth, its legacy lingers in the questions it forces us to ask. How do we distinguish between nature's oddities and potential signs of intelligence? And if an alien artifact asterisk were asterisk hidden in plain sight, would we even recognize it, or dismiss it as just another piece of space junk? The answers might not lie in conspiracy theories, but they remind us to keep looking up, questioning, and separating the stars' true mysteries from the shadows we cast upon them. Asterisk asterisk script segment. Asterisk asterisk imagine a civilization so advanced, it doesn't just build cities or ships, it rewrites the architecture of stars themselves. This isn't science fiction. In the shadowy realm of theoretical astrophysics, a radical idea has taken shape that some pulsars might not be natural at all, but asterisk-engineered asterisk stellar megastructures designed to harness the unimaginable energy of neutron stars. The concept hinges on a tantalizing anomaly. While most pulsars emit radiation in predictable patterns, a handful defy expectations. Their energy output fluctuates strangely, as if something were partially obscuring their beams or tapping into their power. In one Arecibo study, researchers noted pulsars with shadows in their emission profiles, gaps that don't align with known astrophysical processes. Could these be signatures of colossal constructs, like Dyson spheres, built around the pulsar to siphon its fury? Dyson spheres' hypothetical shells enclosing stars to capture their energy are usually imagined around sun-like stars, but a neutron star's energy dwarfs anything an ordinary star could produce. A single pulsar emits enough radiation in a second to power human civilization for centuries. For a civilization mastering interstellar engineering, encasing one would be like plugging into the universe's ultimate power grid. Here's where it gets even wilder. Some theorists propose that advanced beings might not just asterisk harness asterisk pulsars, they could asterisk modify asterisk them. By manipulating a neutron star's magnetic field or crust, they might imprint artificial patterns onto its pulses, turning it into a galactic-scale transmitter. It's the ultimate cosmic sleight of hand, hiding a message not in the noise, but in the very fabric of a seemingly natural phenomenon. Of course, skepticism runs deep. Mainstream astrophysics argues that odd pulsar emissions can stem from starquakes, magnetic reconnection, or interactions with rogue asteroids. Yet the megastructure hypothesis lingers because it challenges us to rethink the limits of natural law. If a pulsar's behavior strays just asterisk outside asterisk, the expected, how do we decide whether we're seeing physics or something far more extraordinary? Perhaps the most compelling case lies in Pulsar J094139, a pulsar whose erratic dimming matches no known stellar process. One paper likened its flickering to a strobe light behind a rotating fan, as if something were intermittently blocking its beams. Natural, probably. But until we rule out every possibility, the question remains, Could some pulsars be cosmic power plants, their rhythms not just nature's handiwork, but someone else's engineering? Whether fact or fringe, the theory forces a humbling perspective. The universe is under no obligation to conform to our assumptions, and if neutron stars can be harnessed, their pulses might carry more than just physics. They could be the hum of machines we're only beginning to imagine. Script segment. What if the universe's most mysterious beacons aren't just broadcasting signals, tapping into the very fabric of reality itself? At the cutting edge of astrophysics, a bold hypothesis suggests pulsars might be doing something even stranger than we imagined, using quantum entanglement to send information faster than light. Forget radio waves or laser pulses. This would be communication that defies Einstein's cosmic speed limit, a potential loophole written into the laws of physics. The idea hinges on one of quantum mechanics' most mind-bending phenomena, entanglement. When two particles become entangled, their properties link instantly, no matter how far apart they are. Change one, and the other responds immediately even if they're on opposite sides of the galaxy. It's as if the universe secretly wired them together, bypassing the need for signals to crawl across space at light speed. Now, imagine a civilization advanced enough to exploit this. If they could entangle particles on a galactic scale, they might embed them in pulsars' beams, turning these dead stars into quantum transmitters. A pulse from one neutron star could trigger an instantaneous change in its entangled counterpart light years away, effectively creating a real-time messaging system across the cosmos. No waiting centuries for a reply, just instant, untappable communication. Wild as it sounds, the math doesn't outright forbid it. Quantum entanglement has already been proven in labs on Earth, with particles reacting in sync across distances of hundreds of miles. Scale that up to stellar proportions, and the implications are staggering. A network of entangled pulsars could function like a celestial internet, with each glitch or timing anomaly serving as a coded packet of data. Of course, skeptics pounce on the hurdles. Maintaining entanglement across interstellar space would mean shielding particles from decoherence, the quantum equivalent of static, for millennia. Then there's the challenge of deliberately altering a pulsar's spin to encode information without disrupting its natural physics. Even if it's theoretically possible, nature might have beaten us to it. Some researchers speculate that neutron stars' extreme magnetic fields could naturally entangle particles in their vicinity, creating accidental quantum channels. But here's the tantalizing thought. If such a system exists, we might already be detecting its fingerprints, those strange pulsar glitches and nulling events. They could be more than just stellar hiccups. They might be fragments of a conversation we're only beginning to eavesdrop on. Whether the product of nature or design, the mere possibility forces us to rethink what these cosmic lighthouses are truly capable of. And in a universe where the rules are still being written, that's a mystery worth chasing. Script segment. Ancient cultures often left us clues about the cosmos hidden in myths, carvings, and sacred texts. But some of these clues seem to defy explanation. Take the Dogon people of Mali, who have long spoken of a companion star orbiting Sirius, invisible to the naked eye. What makes this extraordinary is that modern astronomy only confirmed Sirius B, a dense white dwarf star, in the 19th century. Yet according to anthropologists, the Dogon described its elliptical orbit and even its 50-year rotation cycle centuries earlier. How could a tribe with no telescopes possess such precise knowledge? some researchers point to an even more provocative connection. The Dogon's oral traditions don't just describe Sirius B, they speak of a third star in the system, which they call M. While astronomers haven't found evidence of this hypothetical star, the description bears an eerie resemblance to another cosmic phenomenon, a pulsar. The Dogon reportedly called it the seat of the star that revolves, a dense, spinning object emitting energy almost like a neutron star's lighthouse beam. Could this be a cultural memory of pulsars, passed down from an ancient encounter with starfarers? Skeptics argue the Dogon's knowledge might have been influenced by early contact with Western astronomers or misreported by researchers. But the mystery deepens when we look elsewhere. In ancient Sumerian texts, the god Enki was said to possess a tablet of destinies that emitted a terrible radiance, a description some liken to a pulsar's rhythmic flashes. Meanwhile, Hindu scriptures reference Ashvin's celestial twins who rode a fiery chariot that blinked like an eye, a possible metaphor for a binary pulsar system. These tantalizing parallels raise a haunting question. If pulsars are as visible to modern radio telescopes as campfires in the night, why wouldn't an advanced interstellar visitor use them as reference points? A civilization capable of crossing light years might encode navigational markers in myth, teaching star maps through storytelling. The Dogon's Sirius lore could be one fragment of a much older, interstellar cartography, way to preserve celestial knowledge without technology. Of course, mainstream scholars caution against overinterpretation. Cultural stories often weave natural observations with symbolism, and without concrete evidence, the line between coincidence and contact remains blurred. But the enduring allure of these connections lies in what they force us to confront, that the universe's greatest mysteries might not just lie ahead of us in the stars, but behind us, hidden in the very stories we've told since the dawn of time. Here's your next segment, crafted to flow naturally from the previous discussions while introducing fresh perspectives and maintaining engagement. Close your eyes for a moment and listen. What reaches us from across the cosmos isn't just silence, it's rhythm. Scientists have long converted pulsar signals into audio, translating their rapid pulses into sound waves we can hear. And the results? Chillingly familiar. These cosmic heartbeats don't just tick asterisk, they crackle like static, click like Morse code, or pound with the cadence of a drum circle echoing through the void. Take the Vela pulsar, for example. Its signal, sped up to human hearing range, becomes a rapid-fire staccato 11 beats per second, sharp and mechanical, like a telegraph key tapping out a message. Or the slower, deeper thumps of the Crab pulsar, each pulse landing with the weight of a bass drum, spaced by fractions of a second, so precise they could have been programmed by a machine. It's no wonder early researchers, hearing these sounds for the first time, briefly wondered if they'd stumbled upon a galactic radio station. But the eeriest examples come from pulsars, whose rhythms seem to almost asterisk form patterns. Some mimic prime number sequences clusters of pulses spaced by 2, 3, 5 beats, as if counting in mathematical code. Others produce dual tones, a high-low alternation that evokes binary. When played back-to-back, certain pulsars even create melodic intervals, like the opening notes of a song half remembered. Of course, the rational explanation is physics. These are the sounds of spinning neutron stars, their magnetic poles sweeping radiation across our telescopes like a lighthouse beam grazing the shore. Yet the resemblance to communication is uncanny. In the 1970s, astronomers like Frank Drake of the famous Drake equation explored this very idea. Could pulsars be nature's approximation of an alien broadcast? To test it, researchers have fed pulsar data into signal detection algorithms designed to spot artificial patterns. So far, nothing conclusive, but the exercise reveals something profound. Even if these sounds are purely natural, they've become a Rosetta Stone for how we imagine extraterrestrial messages might sound. There's a haunting beauty to these cosmic rhythms. They remind us that the universe isn't just a silent movie, it's a symphony of particle collisions, magnetic shudders, and dying stars, each with its own voice. And while we now understand the science behind these pulses, part of us still leans in, listening past the noise, wondering if someday, just maybe, we'll catch a beat that wasn't meant for the stars alone. This segment keeps the narrative flowing, grounds abstract concepts in sensory experience, and maintains intrigue without overpromising. Let me know if you'd like any refinements. Some of the most startling discoveries about pulsars haven't come from distant radio telescopes, but from a suitcase-sized instrument mounted on the International Space Station. Since 2017, NASA's Neutron Star Interior Composition Explorer, or NICER, has been pressed against the station's hull like a stethoscope on the cosmos, listening to the faintest murmurs of these collapsed stars. And what it's found has rewritten the textbooks. Take Pulsar J0030 plus 0451, a pulsar 100 light-years away. NICER ultra-sensitive X-ray eyes revealed something baffling. Instead of the twin hotspots predicted by models, one at each magnetic pole, this star had *3*, arranged in a lopsided triangle. That's like finding a refrigerator magnet with extra poles where physics says they shouldn't exist. Even stranger, all three blazed at slightly different temperatures, as if someone had dialed up the heat unevenly across the star's surface. Mainstream astrophysicists scrambled for explanations. Maybe the magnetic fields of neutron stars are more tangled than we thought, like a ball of yarn knotted by a cat. Or perhaps the unfathomable pressures inside these corpses twist their surfaces into shapes we can't yet simulate. But conspiracy theorists saw something else entirely, a symmetry too precise to be random. If nature abhors lopsidedness, as physics often suggests, could those odd hot spots be the handiwork of something or someone else? The speculation doesn't end there. NICER scans of other pulsars found patches where temperatures fluctuated in ways that defied simple cooling models, as if hidden furnaces were flickering beneath the crust. One paper even noted geometric anomalies in emission patterns, subtle distortions that looked less like natural imperfections and more like shadows cast by colossal structures. Of course, the scientific consensus leans toward exotic physics, ultra-dense mountains on the neutron star's surface, or rivers of superfluid neutrons sloshing beneath. Yet the sheer unlikeliness of these features keeps alternative theories alive. What makes NICER findings so electrifying isn't just the data, it's the timing. As we inch closer to unlocking quantum gravity and the secrets of matter at nuclear densities, each pulsar anomaly forces us to ask, are we seeing the limits of known physics, or the edges of something far more profound? For now, NASA's mission continues, its tiny X-ray eyes peeling back layers of a mystery that, hotspot by hotspot, blurs the line between cosmic wonder and cosmic design. Script segment. The universe is unimaginably vast, home to billions of galaxies, each brimming with stars and potentially habitable worlds. With odds like that, the math suggests we shouldn't be alone. Yet, the cosmos remains eerily quiet. This is the Fermi paradox. If intelligent life is out there, where is everyone? Maybe we've been looking in the wrong places. Instead of scanning empty space for fleeting radio signals, what if advanced civilizations aren't broadcasting randomly at all, but using the universe's own megaphones to be heard? Enter pulsars. These spinning neutron stars emit beams of radiation so powerful they can be detected across galaxies, flashing with a precision that puts our best atomic clocks to shame. If you wanted to send a message that could outlast civilizations and pierce through interstellar noise, these cosmic lighthouses would be the perfect medium. No need to build a transmitter from scratch, just repurpose nature's own signal towers. Here's where the paradox takes a twist. Imagine a galaxy where intelligent species have risen and fallen countless times over billions of years. If even one of them had tapped into pulsars as communication relays, their signals would still be pulsing long after their extinction, like ancient voicemails drifting through space. Yet we haven't found any obvious signs of engineered patterns in pulsar emissions. Does that mean no one's out there, or that we're not listening the right way? Some theorists argue that advanced beings might not use obvious Morse code or binary in their messages. Instead, they could embed data in subtle tweaks, tiny delays between pulses, slight variations in beam intensity, or even quantum fluctuations in the neutron star's crust. These wouldn't stand out as artificial at first glance, but to a civilization that knows what to look for, they might scream asterisk, "We're here." Asterisk, others counter that pulsars are simply too extreme to tamper with. The energy required to alter a neutron star's spin or magnetic field would dwarf anything a species could harness, unless they've mastered physics far beyond our understanding. But that's the paradox's cruel irony. If aliens asterisk are asterisk leveraging pulsars, their technology might be so advanced, their signals indistinguishable from natural phenomena to our primitive instruments. So where does that leave us? The absence of obvious pulsar codes doesn't disprove alien existence. It might just mean we're still learning the universe's language. Until we decipher the full spectrum of neutron star behavior, their pulses will remain both a scientific marvel and a cosmic riddle. And if the answer to Fermi's famous question is hiding in plain sight, woven into the heartbeat of dead stars, that might be the universe's greatest irony of all. Asterisk asterisk script segment. Asterisk asterisk, for every bold theory that pulses with possibility, there's a sobering voice reminding us to check our assumptions. Mainstream science approaches the idea of pulsar codes with healthy skepticism, not to dismiss imagination, but to ground speculation in the rigorous standards of evidence. When confronted with anomalies in neutron star behavior, researchers wield a simple but powerful tool, Occam's razor, the principle that the simplest explanation, the one requiring the fewest leaps, is usually correct. And in the case of pulsars, the simplest answer is that their quirks stem from extreme physics, not extraterrestrial engineering. Take those eerie pulsar glitches, where spin rates abruptly change. While they might seem deliberate, astrophysicists point to the chaotic environment inside a neutron star. Picture a city-sized orb of ultra-dense matter, its crust under unimaginable strain, its core a swirling soup of superfluid neutrons. When the crust fractures or the superfluid vortices rearrange, the star's rotation stumbles like a spinning ice skater tucking in their arms unexpectedly. No alien intervention needed, just nature's unfathomable forces at work. Then there's the matter of patterns, prime numbers, Fibonacci sequences, or golden ratios hidden in pulse intervals. Mathematicians caution that in any vast dataset, apparent order will inevitably emerge by chance. Flip a coin long enough, and you'll eventually get 10 heads in a row. The same goes for pulsars. With thousands of these objects flashing across the cosmos, some will appear asterisk to encode meaningful sequences purely through randomness. Without repeatable, verifiable anomalies that defy natural models, these patterns remain intriguing coincidences, not proof of design. Perhaps the most damning critique is the sheer energy required to manipulate a pulsar's signals. Neutron stars are cosmic monsters, their magnetic fields trillions of times stronger than Earth's, their gravity so intense it bends light into knots. For a civilization to imprint messages onto such behemoths, they'd need technology harnessing energies beyond anything physics currently allows. As astrophysicist Carl Sagan once noted, extraordinary claims demand extraordinary evidence, and so far, pulsar anomalies fit comfortably within the extraordinary, but natural, behavior of dead stars. This isn't to say the mystery isn't worth pursuing. Science thrives on questioning the unknown, but until we find a pulsar whose pulses spell out, say, the first 100 digits of pi in binary, or until a signal defies every natural explanation, the cosmic jury's verdict remains clear: pulsars are nature's masterpieces, not messages. They challenge us to dig deeper into physics, not presuppose galactic pen pals. After all, the universe is strange enough without adding aliens to the equation. But then again, as any good scientist will admit, absence of evidence isn't evidence of absence. The search continues. Script segment. The universe has a habit of crafting order from chaos, spiral galaxies swirling into perfect symmetry, snowflakes forming intricate patterns from random moisture. So, when we encounter pulsars ticking away with mathematical precision, it's tempting to chalk it up to nature's genius. But could some patterns be too precise? This is the heart of the debate. Are these cosmic rhythms simply the work of magnetospheric physics, or do they cross into territory where intelligence can't be ruled out? On one side, physicists point to the extreme environments of neutron stars. These objects aren't just dense, they're laboratories of quantum weirdness, where magnetic fields twist into braids hotter than supernova and particle beams ricochet like pinballs. In conditions like these, complex pulse patterns could easily emerge without any guiding hand. Take nulling pulsars, which skip beats unpredictably. Researchers model this as spark gaps in the star's magnetosphere, like a flickering light bulb short-circuiting under too much voltage. No mystery, just physics pushed to its limits. Yet critics highlight anomalies that strain natural explanations. Certain pulsars emit pulses spaced at intervals matching prime numbers, a pattern less likely to arise from turbulence than, say, a deliberate attempt to signal. Prime numbers are universal, unambiguous. They don't depend on language or math systems. If you wanted to broadcast, we're here, across the cosmos. Encoding primes into pulsar pulses would be a brilliant strategy. The odds of such sequences appearing by chance, statistically slim, though not impossible. The debate sharpens when we examine redundancy. Natural phenomena rarely repeat identical patterns across multiple pulsars, yet some exhibit eerily similar timing quirks. It's the difference between finding one clock that's slightly off and discovering a room full of clocks all ticking in the same irregular rhythm. Coincidence? Perhaps, but the longer the list of coincidences grows, the harder it becomes to dismiss the question outright. Skeptics counter with Occam's razor, the simpler answer. that we're still learning Neutron star's full range of behaviors is more plausible than invoking alien engineers. After all, pulsars were only discovered in the 1960s. Our models of their physics are still evolving. What seems improbable today might be textbook science tomorrow. But here's the twist: science thrives on anomalies. If every oddity were dismissed as just physics we don't get yet, we'd never uncover deeper truths. The middle ground: keep cataloging pulsar patterns without presumption. Whether natural or artificial, their secrets are worth decoding, because if the universe asterisk is asterisk whispering to us, the only way to know is to listen closer. Here's your next segment. Picture a crowded dance floor in the cosmos, not of stars, but of their spinning corpses, flashing in eerie unison. Deep within globular clusters, ancient swarms of stars bound together by gravity, astronomers have found something extraordinary: multiple pulsars blinking in seemingly coordinated rhythms. These dense stellar cities host hundreds of thousands of stars packed into a space smaller than our solar system, and among them, neutron stars appear to sync up in ways that defy simple chance. Could this be nature's most elaborate coincidence, or something far more intentional? Take the globular cluster Terzan 5, a glittering knot of stars near the Milky Way's core. Inside, at least 30 pulsars spin at wildly different speeds, some completing hundreds of rotations per second, others lumbering along with leisurely ticks. Yet when researchers mapped their pulses, odd patterns emerged. A handful of these pulsars exhibit nearly identical timing glitches, their spins stuttering within days or weeks of one another, despite being light years apart. It's as if invisible threads connect them, orchestrating their hiccups like a conductor guiding an orchestra. Mainstream astrophysics has explanations, of course. In such crowded environments, neutron stars might share material or gravitational nudges, subtly influencing each other's behavior. Or perhaps the cluster's collective magnetic field, a tangled web stretching across the entire region, triggers synchronized quakes in their crusts. But skeptics point out the statistical unlikelihood. For pulsars with such diverse spins and ages to glitch in near unison suggests a level of coordination that turbulence alone can't easily explain. This is where the network theory ignites debate. If an advanced civilization sought to build a galaxy-wide communication system, manipulating pulsars in a densely packed cluster would be brutally efficient. Like a string of lighthouses flashing in sequence, their combined signals could relay information across vast distances, with each synchronized pulse acting as a node in a cosmic internet. Even more provocative, globular clusters are among the oldest structures in the universe. If someone had engineered such a network, it might have been humming for billions of years before Earth even formed. Yet for all its intrigue, the idea faces steep hurdles. Pulsars in clusters interact naturally, and their odd alignments might simply reflect environments more chaotic than we yet understand. What's undeniable, though, is how these stellar syncopations push us to rethink the boundaries of natural law. Whether the product of extreme physics or something beyond our current grasp, pulsar clusters remind us that the universe's greatest mysteries often lie not in isolation, but in the spaces between. This segment balances scientific plausibility with open-ended wonder, avoids repetition, and maintains a crisp pace. Let me know if you'd like any refinements. In the quiet hum of supercomputers and radio telescopes, a new kind of cosmic detective work is unfolding, one that treats pulsar signals not just as astrophysical phenomena, but as potential puzzles waiting to be solved. Across research labs and universities, teams are applying techniques normally reserved for cracking ancient ciphers or deciphering enemy codes to the rhythmic pulses of neutron stars. What if these signals aren't just cosmic noise, but a language we haven't learned to read yet? Take the Breakthrough Listen project, which has repurposed its AI-driven algorithms originally designed to scan for extraterrestrial radio transmissions, to analyze pulsar data for hidden structures. Machine learning models sift through terabytes of pulsar emissions, hunting for deviations from natural randomness, repeating sequences, geometric progressions, or clusters of pulses that resemble mathematical constants. In one experiment, researchers trained neural networks to flag anything in the data that looked too ordered, like finding a perfectly shaped snowflake in a blizzard. So far, no smoking gun, but the very attempt rewrites how we approach the cosmos. Other efforts go even further. At the University of California, Berkeley, scientists have borrowed methods from cryptography to test whether pulsar pulses could carry embedded information. Imagine treating each pulse like a binary digit, a 1 or a 0, then searching for patterns that might form a rudimentary message. Some teams have even applied Fourier transforms, a mathematical tool used to untangle complex signals, to see if pulsar rhythms hide higher dimensional structures when analyzed at different scales. The results, a mix of tantalizing near misses and dead ends. One pulsar's pulse intervals briefly hinted at the first few prime numbers until deeper analysis revealed it was a statistical fluke. What makes these efforts revolutionary isn't just the technology, but the shift in perspective. For decades, pulsars were seen as celestial lighthouses, beautiful but impersonal. Now we're probing them like artifacts, asking not just asterisk how asterisk they work, but asterisk what they might be saying asterisk. Critics argue it's a modern-day Rorschach test. We're projecting meaning onto cosmic static. Yet proponents counter that if we asterisk don't asterisk look, we might miss the one signal that isn't random. The most intriguing work comes from collaborations blending astrophysics and computer science. A recent SETI project used generative AI to simulate what an artificial pulsar signal might look like, then compared it to real data. The goal, to see if any known pulsars match the hallmarks of engineered patterns. While no matches emerged, the study revealed something unexpected: natural pulsar emissions, sometimes asterisk mimic asterisk synthetic ones, so closely that even AI struggles to tell them apart. That blurry line between nature and design might be the most important clue of all. Of course, skeptics remind us that absence of evidence isn't evidence of aliens. But the very act of searching refines our understanding. Every algorithm tuned, every pattern dismissed or flagged, brings us closer to answering a question that hums beneath all this research. In a universe this vast, how would we even recognize a message if it were staring us in the face? For now, the computers keep listening, sorting the cosmos into two piles: the brilliantly random and the whispers we can't yet explain. Asterisk asterisk script segment. Asterisk asterisk Hollywood has always had a love affair with the cosmos, but few celestial objects capture the imagination quite like pulsars, especially when they're framed as cosmic messages from beyond. Take asterisk Contact asterisk, the 1997 film based on Carl Sagan's novel, where astronomers discover a pulsar's radio pulses contain a hidden blueprint for humanity's first interstellar machine. The idea that a neutron star's rhythmic beats could carry deliberate instructions, blueprints, etched into the fabric of spacetime turned astrophysics into high-stakes drama. It's a premise that lingers because it taps into our deepest wonder. Asterisk, what if the universe is trying to tell us something? Asterisk, gaming worlds have embraced the same mystery. In Asterisk Destiny, 2 Asterisk, the warmind Rasputin, an ancient AI, designed to protect humanity, uses pulsar signals as a cryptographic key, treating these dead stars as celestial Rosetta Stones. The game's lore suggests pulsars aren't just navigational tools, but literal archives, their pulses encoding lost knowledge from a long-vanished civilization. It's a fantastical twist, yet one rooted in real scientific speculation, that advanced beings might repurpose neutron stars as galactic hard drives. Literature, too, has woven pulsars into stories of cosmic conversation. Arthur C. Clarke's Asterisk, The Light of Other Days Asterisk, imagines a future where humanity taps into pulsar emissions to peer across time and space, treating their beams as windows into other realities. Clarke, known for blending hard science with visionary fiction, framed pulsars not just as natural phenomena, but as bridges, potential conduits for communication transcending the limits of light's speed. What unites these fictional portrayals is their willingness to blur the line between science and myth. Pulsars, with their eerie regularity and unfathomable energy, become more than stellar remnants. They're cast as cosmic intermediaries, relics of a universe that might still be speaking, if only we knew how to listen. Even as astrophysics demystifies these objects, pop culture keeps the question alive. Asterisk, could the universe's most precise rhythms still hide a whisper of intent? Asterisk, of course, scientists remind us that pulsars obey natural laws, not screenplays. But the persistence of these stories reveals something profound about us. Pulsars, whether in films, games, or novels, reflect humanity's enduring hope that we're not just observers of the cosmos, we're participants in a conversation that began long before us, written in the pulses of dead stars. As humanity stands on the brink of a new era in cosmic exploration, the next generation of telescopes is poised to revolutionize how we listen to the universe's most enigmatic signals. Leading the charge is Breakthrough Listen, the most ambitious scientific program ever designed to hunt for extraterrestrial intelligence, now setting its sights squarely on pulsars. With cutting-edge instruments like China's 500-meter aperture spherical telescope, FAST, and the upcoming square-kilometer array, SCA, we're not just upgrading our tools, we're rewiring how we interrogate the cosmos. FAST, with its staggering dish spanning half a kilometer, acts like a cosmic ear pressed against the galaxy's heartbeat. Already, it's detected over 500 new pulsars, some with pulse patterns so peculiar they've reignited the debate over natural versus artificial origins. But the real game-changer comes when FAST collaborates with Breakthrough Listen's AI-driven algorithms, which can analyze decades of pulsar data in days, flagging anomalies human researchers might miss. Imagine scanning every tick and glitch from thousands of neutron stars, searching for the faintest statistical whisper of something intentional. Then there's the SKA, a global effort to build the largest radio telescope array in history, spanning continents from Australia to Africa. When operational, its sensitivity will dwarf all existing telescopes combined, allowing it to detect pulsar emissions 10 times fainter than current limits. More crucially, SKA's resolution will let scientists map the asterisk shape asterisk of pulsar beams in unprecedented detail. If those beams contain subtle aberrations, asymmetries, or intensity variations that defy astrophysical models, it could suggest something is asterisk modulating asterisk them. Breakthrough Listen's pulsar initiatives go even further. One audacious project involves monitoring, nulling pulsars, those that periodically go silent, for non-random patterns in their pauses. Another plans to test whether certain pulse intervals could transmit data via quantum fluctuations, exploiting the bizarre physics of neutron stars themselves. These aren't just experiments, they're stress tests for reality, probing whether the universe's most precise clocks might also be its most sophisticated messengers. Yet for all their power, these telescopes face a paradox. The more data they collect, the harder it becomes to distinguish between nature's chaos and potential design. A glitch in one pulsar might be a starquake. The same glitch repeated across dozens could hint at something else entirely. That's why projects like Breakthrough employ triangulation of skepticism, cross-checking anomalies against multiple instruments to filter out wishful thinking. The goal isn't just to find signals, it's to ensure that if we ever do, the discovery withstands every conceivable doubt. What makes this moment unique isn't just the technology, but the philosophical shift it represents. For centuries, we've treated pulsars as celestial wonders to observe. Now, we're learning to interrogate them. Whether they're natural marvels or something more, the answers, or the next layer of questions, are closer than ever. And if the stars asterisk are asterisk speaking, we're finally building the tools to hear them. Asterisk asterisk, script segment. Asterisk asterisk, there's an unsettling thought lurking behind the search for cosmic messages. What if we're not just listening, but being heard? The moment we detect a potential signal encoded in a pulsar's rhythm, humanity faces a dilemma older than radio telescopes. Should we reply? It's a question that splits scientists down the middle, balancing curiosity against caution in a debate that feels ripped from science fiction, yet the stakes couldn't be more real. On one side, visionaries argue that answering a pulsar's call could be the greatest leap in our species' history. If an advanced civilization engineered these signals, they might hold knowledge far beyond our own blueprints for clean energy, medical breakthroughs, or even warnings about cosmic threats. The late Stephen Hawking once compared ignoring such an opportunity to indigenous cultures shunning Columbus's ships, fearful of the unknown. Silence, in this view, is stagnation. But the counterargument is chilling. Imagine a universe teeming with civilizations, all hiding in cosmic silence, not out of isolation, but survival. This is the core of the asterisk dark forest theory asterisk, a concept from Liu Cixin's sci-fi epic that's gained traction among astrobiologists. It suggests every advanced species stays quiet because broadcasting your location is suicidal. You never know who or what might be listening. If pulsar patterns asterisk were asterisk artificial, replying could amount to ringing a dinner bell in an invisible jungle. The risks aren't just theoretical. In 1974, the Arecibo message beamed human details toward a star cluster, a gesture critics called reckless. Today, organizations like SETI messaging extraterrestrial intelligence push for active transmission, while the SETI Institute's majority opposes it, favoring passive listening. The divide hinges on an unanswerable question: are potential allies or predators more likely to decode our signals? Protocols exist, albeit loosely. The International Academy of Astronautics suggests global consensus before any reply, but no enforcement mechanism binds nations or private entities. A single rogue transmission, say, from a billionaire's backyard antenna, could theoretically expose Earth without oversight. Meanwhile, scientists like David Brin propose middle ground solutions, sending abstract math or physics constants first, avoiding specifics about our location or biology. Perhaps the greatest irony is this: pulsars, whether natural or engineered, might already be the universe's compromise. Their signals are omnidirectional, meaning any civilization could detect them, but their very permanence makes them neutral ground. Unlike a targeted message, they don't betray who is listening, only that someone might be. In that sense, they could be the cosmic equivalent of a message in a bottle, meant to be found but not traced. The debate won't resolve soon, but as telescopes grow more powerful, the day may come when a pulsar's pulse holds a pattern too deliberate to ignore. When it does, humanity will face a choice: to reach back into the void or heed the ancient instinct to hide. Either way, the decision will echo far beyond our lifetimes, written in the stars we dared to answer, or the silence we chose to keep. As we reach the end of this cosmic journey, the enigma of pulsars lingers like an unsolved riddle written in starlight. On one hand, these spinning neutron stars are undeniably nature's masterpieces, celestial metronomes, whose rhythms have guided our understanding of gravity, matter, and the fabric of space-time. Their precise pulses align flawlessly with the laws of physics, each glitch and wobble explainable by the turbulent chaos beneath their surfaces. For most scientists, that's where the story ends. Pulsars are the universe showing off its raw, untamed power. Yet the whispers of possibility persist. Those eerie prime number sequences, the synchronized pulsar clusters, the anomalies in emission patterns that even AI struggles to classify. Could they all really be cosmic coincidences? Or is there a sliver of a chance that some intelligence, somewhere, has imprinted these stellar beacons with signatures we're only beginning to notice? The debate isn't just about aliens, it's about how we define the boundary between the profound and the purposeful. What makes this mystery so compelling is that both perspectives reveal something extraordinary. If pulsars are purely natural, they showcase the universe's ability to create near miraculous order from chaos. If they're more, they could rewrite our place in the cosmos. The truth, as always, likely lies somewhere in the unexplored middle, a space where science keeps probing and imagination keeps questioning. So where do *U* stand? Are pulsars the universe's most dazzling physics experiment? Or could they be something even grander, a message encoded in the stars themselves? Drop your theories in the comments below, and let's keep the conversation as boundless as the cosmos. After all, the greatest discoveries often begin with a simple question.